Hello once again, and welcome to our ongoing look at the unit circle and ultimately angle measure. At this point, we have looked at graphs of sine and cosine, the basics, and we've started transforming those, and we will continue to do more with that in the next class, maybe the next class after that as well. But what I want us to do right now is add one more to the mix. You see, there's not just two trigonometric functions. There's six main ones: sine, cosine, of course. There's tangent, cotangent, secant, and cosecant. Now in this class, I want us to focus just on three, and really on two, really just on sine and cosine, but at the same time, I do want us to be able to graph tangent. So here I have the Cartesian plane of sorts. I do have it scaled nicely. I've got 1 and -1 for scale, and also my x-axis, I have increments of pi. So halfway between is pi over 2, halfway between that and 0 is pi over 4. And that's going to matter here in a bit. Remember also that we had mentioned that tangent, unlike sine and cosine, is periodic with period pi. Whereas sine and cosine have period 2 pi, tangent only has period pi. So let's see if we can get just from 0 to pi and figure out what's going there. Now first of all, I need to find tangent of 0, which is sine of 0 over cosine of 0. Sine of 0 is 0, cosine of 0 is 1, so that is my first point right there. Then comes tangent, oh boy, let's see if I can do this by hand, of pi over 4. And that's sine of pi over 4, which is root 2 over 2, over cosine of pi over 4, which is also root 2 over 2. So we see that the tangent, the ratio of those two values, is 1. Now tangent of pi over 2 is sine over cosine. That's undefined. So I don't have anything here. And the tangent of 3 pi over 4 is now sine over cosine. Sine is positive, root 2 over 2. Cosine is negative. So that ratio is now -1. And then finally I hit sine of pi. And because sine is pi is periodic with 0 here, right, it's period pi, so I actually end up having tangent of pi equaling tangent of 0, or sine of pi is 0, cosine is -1, 0 over -1 is also 0. So here are 4 points I'm looking at right now. The temptation might be there to say, well, here's my tangent wave, but that is not the case at all. Partly because, well, tangent's actually undefined here at pi over 2, so I can't just fill in across it because it's undefined there. The truth of what's going on is just like with the function f of x equaling 1 over x, the ratio of tangent is getting really large. Right, on the unit circle, as we approach pi over 2, so as we get up here, my x value is getting very small, and my y value is getting closer and closer to 1. So this is starting to look like 1 over x as the x gets closer and closer to 0, right? 1 up top, 0 or approaching 0 on the bottom. So what happens to tangent, that ratio, is as we get closer and closer to pi over 2, my ratio gets larger and larger. On the other side of it, though, once we get just slightly past pi over 2, now my x value is negative, and my sine value is still more or less 1, so 1 over a very small negative number ends up being a very large positive number. And if you were to keep going with this, you would end up with the true graph of tangent. Oops, something looks off about that. That's pi over 2 there. There's pi. Okay, I know what I did wrong. It was mostly right, except we keep going like that. And that is the graph of tangent. If you're looking for vocabulary words, right here, where it's undefined, I have what's called a vertical asymptote. You'll learn more about those in precalculus algebra. But we have vertical asymptotes there because the graph gets closer and closer to these lines, but they never quite touch. And that's really all there is to say. That's what tangent looks like. Oops. So picking up from there, just to prove I'm not crazy, let's actually graph on Desmos the full formal graph, and there it is. We have this pattern, these swooshes, whatever you want to call them, repeated forever, and every pi over 2, every odd pi over 2 is a vertical asymptote. So the whole thing has period pi. So one way we drew that was to go from negative pi over 2 to positive pi over 2, which incidentally is going to coincide with something that we'll see very soon when we get to inverse trigonometry. But you could go from 0 to pi and just have it start from here, go up, skip back down and go up. Any way you choose to draw a period is fine, provided at the end of the day you get a graph that looks like this. This is tangent. Note also that you can't just plot a whole bunch of points and get a nice, accurate graph of tangent. You have to remember what happens as you approach being undefined there. As you get closer and closer to dividing by 0, the outputs get larger and larger. So that's one thing you have to keep up with, and just connecting dots might not get you there. Also, one nitpick, and we'll be pretty much done with this, it is that tangent, unlike sine and cosine, actually all the 4 other trig functions, don't have amplitude. Right? Amplitude is the distance from a median line to its peak or to its valley, and tangent doesn't have a peak, doesn't have a valley. It keeps going up forever, it keeps going down forever. Amplitude is a meaningless concept for tangent. And so if you had a function like f of x equaling 2 tangent of x, well, our transformation rules still apply. I still double my outputs. I'm still stretching it by a factor of 2, but it is not correct to say this has amplitude of 2. It does not. It does still have a period, and that period is still pi, but it doesn't have amplitude, period. Well, it doesn't have amplitude, full stop. There we go. So here's what I want us to take away from all this. Strictly speaking as an educator, the reason why we have you do transformations, it's not so you can memorize a bunch of rules. That's not the reason. You can do that, and for all intents and purposes, you'll have similar levels of success in this course, but the real reason why we teach transformations, why we cover the idea of transforming a known function into another less known function, is because that's what people do. We use applications, we take real-world problems, real-world applications, and we use known functions to model those phenomena. Usually sine and cosine, but tangent can be done with that as well. And so, from that perspective, we go over all these transformations. So you can do exactly that. The other reason, to be more abstract, is just we want you to think about what changes are affected by certain differences of functions. So how does this change affect my function? What is the effect of this cause? What is cause and effect going to work out to be? That's why we do this. I mean, if you choose to believe it's because we just want you to memorize rules, well, so be it. But I tell you now, and we'll see as we go forward, that that's not the case. We really do it so that we would be more comfortable doing changes of real-world behaviors and doing changes just for the sake of doing them mentally. That's really it. So in this particular section, what I want us to be able to do by the end of it, after our class time, is to be able to use the same transformation rules we covered for sine and cosine and apply them now also to the graph of tangent. And that's it. So let me know what you think about that, and I will see you in the next class. You guys have a good one.